Thrilled to be here. And yeah, thank you everyone for being here to listen. And today I'm here to talk about the data error generating process. As Rohan somehow alluded to, part of my interest in kind of the complexities that come with working with real world data. And what I want to kind of argue today is that by better understanding the kind of mechanics and the guts of the data engineering and the data generating process for our data, we can drive better, more meaningful data quality tests. So first, I'd ask you to think briefly, what if we were monitoring, instead of a data set, trying to detect errors in a real world system? We'd probably start by thinking about the ways things could go wrong, like derailments or collisions that are super high impact, and work backwards from that, thinking about the kind of things that we'd want to have to detect in our system that might cause those problems, like trains being on the same track at the same time, or part of that track being damaged. We wouldn't overly focus on things like very low probability events, such as all passengers sitting on the same side of the train and it tipping over. And we wouldn't inherit too much simply from industry best practices, like landing gears getting stuck, when important to worry about for a plane, but not for a train. However, I often feel that this same level of detailed thinking doesn't always apply when we go to monitor and assess and validate our data quality. I often see chucks in this space end up on two ends of a broad spectrum. There's kind of the intelligence-free world, where we're applying very rote summary statistics and EDA, maybe doing nulls and duplicate counts, but doing it a little bit mindlessly. Or on the other end of the spectrum, there are a lot of very fancy, very elaborate artificial intelligence methods now being shipped in a lot of modern tools that do things like anomaly detection as a way to detect data quality. But I argue there's this kind of missing gap in the middle of really implying human intelligence in a more hypothesis-driven approach and understanding the data generating process in the same way that you might understand it for building a model that's supposed to capture that process, but instead for our purpose, using it to detect the errors in the process. And to give kind of just like and as kind of like analysts, I think we're the best and most equipped of anyone to kind of do this process, because we really sit in the middle of all of the numerous handoffs data goes through, from the real world actual processes that are generating it, how it's collected and atomized into digital quantities, how it's loaded and moved between systems, and finally, how we're transforming it for our work. And along this process, I think we need to be asking always two key questions. First, in that last mile of transformation, what do you need to be true of your data to trust it for your analysis? And based on that, what are the likely failure modes at any of these steps higher in the process that could prevent these things from being true? So to just take a very trivial high-level example, we've probably all seen many different ways the data can be missing and the data loads can fail. Compared to kind of a universe with very complete data, we can have stale data where the data just simply stop loading to our data set sooner than we expected. That might happen for a complete day, or it might happen somewhere in the middle of the day. A load could fail part of the way through, which might make it harder to detect. If our data is coming from multiple sources, those sources might be jagged, some might continue longer than others, or we could have situations where part of our data had stopped loading earlier in the process and restarted, or we might have even loaded that data multiple times. Truly anything can happen. And however, if we just start thinking about how do I know my data is complete, we might rely on a very basic check, like a recency check, where we check if the maximum date in our data set is either the current date or whatever we expect that maximum date to be. That in some ways is a bit of an industry standard. But if we just relied on that one check, we can catch the stale data use case, but that check alone wouldn't actually catch all of the other kinds of ways that we can have a data load failure. So without that reasoning of thinking about how certain types of data errors occur, just checking for the output isn't really sufficient. And again, tying this more back to statistical methodology, I think there's a really strong parallel here to the ways that we think about MCAR, MNAR, MAR, different types of missingness in our data set, because in the same sense that we're actually reasoning about the mechanics of how our system breaks, that gives us different tools to better detect and better fix them. So bringing this back, I promised I was going to talk about the real world. So it'd be cheating to not kind of use a real world data set to do this. So I wanted to pull down some data from the New York subway system data to further illustrate some of these concepts. This data is collected by every single turnstile throughout the subway system, cumulatively counting up how many times it's been turned. And 4 times daily, that data is uploaded to a centralized server and ultimately published online. So we have this nice panel data structure of every single turnstile at every single period throughout New York City. So the idealized way we'd want to try to think about transforming this data would look something like this. If we wanted to understand how many people were arriving in those subway systems at any given time period, we could start by taking those cumulative entries, first computing a lag to understand how many entries went through each turnstile at each time period, and then finally aggregating those up at whatever grain was of interest to us, whether that be the stations, whether that be across the system. Of course, this alone, these very simple, basic, obvious transformations, the reason I go into so much detail here is it's important to call out, even in this process, we're actually relying on some key assumptions. We're assuming that none of those entries fields are non-missing and that they're all monotonic, that they truly are strictly increasing over time, just as we expect. So with those assumptions, we can start to think about what in our sensors would actually make that break down, what could make that not be true. And so some of the ways we can start to reason about problems literally at the turnstile level. So we might have missing data if a turnstile is broken, or if it somehow stops being able to upload that data to the centralized servers. Or we might have that non-cumulative, non-monotonic data if any given turnstile, for whatever reason, is reset. For example, if it's replaced or has some sort of maintenance event. And with this reasoning process, that can kind of open our minds to different ways that we can structure our data checks, small tweaks to the normal ways that can have a little more power and a little more efficacy. And one specific category of this sort of tweak that I found to be useful is doing checks at a group level. Often many of the common data tests that you think about in terms of uniqueness, minimums, maximums, etc., are a bit underpowered in a way. And simply by adding a grouping dimension to that, especially when you're working with panel data, can be really powerful. Some checks are only expressible at all by the group level. For example, a turnstile ID might not be unique across the system, but it should be unique at the station level. Other checks can be done at the aggregate level, but they're really more rigorous if we add in this grouping dimension. Going back to the previous example we talked about, we can think about the maximum date across the system versus the maximum date for every single source. And finally, sometimes it's just a more semantically helpful crutch to brainstorm what we want to test. So applying this trick to the New York subway data, we can find some interesting phenomenon. First, testing monotonicity, which is only expressible at that grouping level, because of course, turnstiles, if we weave our turnstile data together, aren't necessarily always going to have that monotonic pattern. But within every single turnstile, we'd ideally like to see some trend that looks like this. And we'd like to see that repeated independently for all of the roughly 5,000 turnstiles across the system. However, if we actually conduct this sort of test, we can find a lot of really interesting anomalies. We find that there's some turnstiles that actually do count monotonically over time. They just choose to count down. Or there are others that demonstrate the sort of oscillating pattern that I've shown due to frequent maintenance and replacement events, like I mentioned. Similarly, we can find many examples in this data set where we can have more rigorous tests, like with that missing data maximum date case. there's no date-time combination across the entire data set that's truly missing for every single observation. However, if we conduct this test at the turnstile level, we can see for pretty much any time period between 50 and 100 observations from individual turnstiles are missing, which again could really jeopardize some of our functionality for even just calculating basic entry rates. So in summary, really by doing these two key tests and asking ourselves critically of what do we need to be true of our data in the last mile, and how do those, where are actually the pitfalls and stumbling blocks throughout the data generating process that could keep those things from being true, we can really add a lot more power and rigor to our data analysis, to our data validation, to our data testing, without massively changing our tools, our mindset, or adding a lot of friction to the system. And I believe I'm about at time, so I won't go into this in great detail, but I've included some slides at the end of this deck that there are many nice, this approach is very easy to implement in existing data quality tools, such as the pointblank package, which I'm a big fan of in R. Here we can see that the y variable is not unique, but it is unique when nested within each x variable. Using a basic pointblank rows distinct function, we can see that that test fails if we just try to check our y variable through that property. But with more expressive tests done at the segment level, we can see that we can get that data test to pass. And similarly, I recently implemented a pull request to the dbt utils package, which is part of the dbt ecosystem for building data, that makes it very easy to add this kind of test to a wide variety of the standard kind of boilerplate out of the box tests that they offer. So thank you very much. Really appreciate kind of the time. I hope that is a helpful kind of framework for thinking about really how to focus in on what to test when you're testing your data. I've added some links at the end of this slide deck that if you want to either play with the raw data, very interesting, very, very messy data set, so it can be fun to get a little hands-on. And I've also linked to a couple of related blog posts I've written, both about the data engineering side of the data generating process at a high level, as well as the merits of group checks in particular. Thank you.